Okay, so welcome back. So, maybe you've tested and found out that your moment, the conditional moment test do not apply, okay? Or maybe you don't actually want to do the test and just want to estimate the model that will respond to any specification of the distribution or the shape of the distribution of the error term, but you could potentially estimate it under some weaker assumptions, okay? And then you just compare those parameter estimates with what you got from Topol. So that's what we're going to do now. Okay, turns out we don't really actually need the normality assumption. It's going to give us a lot of power, but for estimating beta, in principle, we don't really need it if we have lots of data. Okay, so we're still interested in the model where we have a latent variable that is x beta plus u. We only observe, y when it's non-censored. So that is whenever, y star is positive. And then the question is, can we estimate beta without imposing normality and dependence between u and x? Okay, just like we did before. These were really strong assumptions that appeared to be have severe consequences for the consistency of the Topol estimator that were violated. And like Obama would said, yes, we can. Yes, we can. There's still hope. We can use conditional moment assumptions. Okay. So what would the assumption be here? It could be, for example, the conditional median of y of u is given x is equal to 0. Now, when we normally, what you see so far have assumed that it's the conditional mean of a variable that is equal to 0 to estimate parameters, just like we would do in the linear regression model and to obtain OLS. But here we actually cannot do that because we really don't observe the observed variable, and we don't want to make assumptions about what the distribution of that error term is in this particular case. So and we need that distribution to actually get the mean. But we actually don't need that to get the median, to figure out what is the conditional median of x given the set of explanatory variables. So what we can do is, instead of basically assuming an entire distribution for this u, we can live with this assumption. Let me just go take a little digress and talk a little bit about the property of the median. Now, median has a very nice property. That is, if you take the median of the nonlinear function of a stochastic variable y, okay, what you get is actually that nonlinear function evaluated at the median if G is monotone, okay? And so it can be completely nonlinear. It doesn't have to be, even differentiable or continuous or anything. It just have to be essentially monotone. You get this expression here. What function do we have? Well, we have the max operator, right? The max operator that is appearing in our model, so we can use this trick. And so really what you get out of this is you take the conditional median of y given x, well, and then you substitute in essentially, I think here there's some stuff going on. I need to break and, add some equality lines. Just a second. Okay, so we're back. I had a quality line here. I was a little confused myself. So anyway, so what we do here is we can use the property of the median to derive basically what is the median of y given x. Okay. So recall that the property of the median is the following. You can take the median of a nonlinear function and basically just take that is equal to the nonlinear function evaluated at the median. Okay. Now, what is our nonlinear function? Well, our nonlinear function here is the max operator. Okay, so here you have essentially y equal to max of 0 and y star. Okay, now as that is traveling directly through the median can just travel directly through. Well, then what you can essentially get is that this median of y, which is, what is y? That is max of 0 and y star. Well, that is the same as essentially taking that function, the max of 0 and y star, and then evaluated the median of y star. Okay, so this is just an application of what is going on right here. Okay, and then since we are taking conditional median given x, we can put x beta outside here. Y star that's equal to x beta plus u. And then we're still left with this conditional median of u given x, okay? And this is by assumption, our identifying assumption is equal to 0. So the conditional median of y given x is equal to x beta. And this we can estimate essentially by median regression, okay? And you know, there's a section that talks about quantile regression in chapter 12 of Woolwich. In this case, we look at the, you know, the 0.5 quantile, the median. And it turns out you can estimate median regressions using something called the least absolute deviations, okay? Where you, instead of minimizing the squared difference between, you know, the observed outcome and our model for that conditional median, well, then you take the absolute difference. This is why it's called the least, we're minimizing, right? Least and absolute deviations. Okay. Actually, whenever I forget one over n here, I apologize for that. This is I just forgot. So this is what you get here. You get this expression here, and that is consistently, that's going to consistently estimate beta. Okay. This is originally suggested by James Powell, and it's often called the Powell estimator for that reason, or the CLAD estimator for censored least absolute deviations. It's least absolute deviations because we are minimizing the least absolute deviations between y and our model for y, okay? And then, or our model for the conditional median of y. And then it's called censored because we have the censoring part here with this, with the max operator sorting out all the observations that are negative, okay? So that's why we call it the CLAD estimator too. Now, just a few words before we actually go and compute this thing. I'm going to make a Python illustration in just a minute. Can Powell's estimator then estimate the quantities of interest? Well, what we can show is that, you know, this Powell estimator is consistently estimating beta, okay? So if you have beta, well, then you have your object of interest in a censored regression model, okay? At least when the distribution of u is symmetric around 0. So if your object of interest is really that regression line, that the conditional mean of y star, well, that is equal to the conditional median if you have a symmetric distribution. Otherwise, what you would estimate would be the conditional median, okay? You just have to be aware that you're potentially different, estimating different things in those cases. Okay? And so that would be equal to x beta. Once you observe x and once you have estimated beta, and we can do so with the CLAD estimator, then you have your object of interest, okay? And you can calculate the partial effects, which would be just equal to beta. That is fine if you're in the world of censoring, such as, you know, the top coding of wealth or censoring in the bottom of some other variable, okay? Now, in the corner solution outcome model, it's clear that from beta, we don't know enough to derive what is the probability that y is equal to 0, or that what the conditional mean is. We need assumptions to basically derive that. What is the distribution of the error term? And without that, there's no hope you can estimate these expectations. Okay, and neither for the unconditional distribution or for the conditional mean, where you're conditioning on y being positive. Okay, these are not identified from these restrictions, so you cannot calculate that. That doesn't mean that this model is not useful in a corner solution outcome context, because in both these cases, you would want to see if beta is giving you the same stuff as Tobit, as you get for Tobit if you estimate with the Powell estimator. So it's actually a good specification test for whether you think the Tobit model is misspecified. Okay, and then basically, if you think that's misspecified, you estimate that the CLAD estimator well, then you might do something to respecify your corner solution outcome model, so it's no longer Tobit. Anyway, so here's a little bit about the asymptotics. It turns out that actually this objective function, the fact that we have working with, instead of the squared difference or basically or the likelihood function that is completely smooth in the parameters, well, now we're working with this absolute deviations and the max operator, that results in kinks in the objective function. There is a kink basically because of the absolute value. Well, that's looking essentially like a V, right? You know, you have X here on the on the X-axis, and then for all the negative values, well, you're just going to get positive values of X. So when X is increasing, well, this is or increasing, you know, becoming less and less negative. This is falling, and then it's increasing afterwards. So it looks like just like a V with two 45-degree lines meeting each other at 0. Okay, so there in the bottom of the V, there is discontinuity. Okay, that is when, you know, this is what is inside this bracket is equal to 0. Okay, in other words, when y is equal to the max of 0 and x beta. Well, you have another discontinuity. That is when xi beta is equal to 0, right? You've seen that kink in the max operator, right? It goes like this, and then it jumps. There's a kink in the bottom of that operator, okay? And so, well, should we worry about this? Well, if you want to do inference based on theorem 12.3, or actually, because I mean, this is an M estimator, right? You know, in principle, you can use that theorem, right? You know, it's for M estimators. Well, that theorem is derived under assumptions about differentiability, and you can see it clearly. Like, for example, in you know, just in the equations there for what the variance covariance looks like. Well, it's all about derivatives, right? First and second order derivatives. So if the function is not differentiable, how do you calculate those? Okay. So that's a problem. So we still have that if, you know, the beta is identifiable, and, you know, your random sampling of all the usual stuff and all the regularity conditions about Borel measurability and blah, 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 then this is going to be en route consistent and asymptotic normal. Okay, but you cannot establish the asymptotic normality and derive the variance covariance matrices from the theorem that's appearing in chapter 12 on the asymptotics normality of M estimators, like theorem 12.3. Fortunately, Powell has a applicable theorem to establish this result. Practically, for you guys, it means that you cannot just differentiate the objective function twice, take the square root of the diagonal, and then you're fine. Okay, you know, after appropriately taking the inverse and divided by it. What you can do is something else. You can, you know, do bootstrapping, and I'm going to talk about how to do that in just a second. Okay. But before that, I'm going to talk about some computational issues that just arise simply just how do you maximize or minimize this objective function that is non-differentiable. Remember, we're using Newton's method or BFGS. All these algorithms, they are relying on being able to compute the derivatives of the objective function. Okay? So this creates some computational issues that you potentially face, and you have to be very careful when you're trying to estimate models that has these non-differentiabilities. So I'm going to talk about some of these computational issues in the next video.